As always, thank you very much for invitation. Well, we're in a, well, I shouldn't say unusual now, it's usual. So we're meeting in the Cameron format, but I would like to say that in spite of that, I would invite all the participants to be as interactive as possible, and wherever there are certain questions or topics they want to be covered, then please don't hesitate.
Yeah, don't worry about that, Vadim. We will interrupt you.
Okay. So the topic of this mini course is random walks and self-similarity. Let me start writing. And okay, and now I discover that somehow there is a problem with screen sharing. Okay, for some reason. Okay, let's see.
But we see your screen very well.
Yes, but I'm not sure I will be able to write on the whole screen.
So we see random walks
and
self-similarity.
Self-similarity, yeah. And self-similarity. So there are two areas about a combination of which I want to talk today. One of them is random walks on groups, and the other one concerns a special class of groups, or rather group presentations, which is called self-similar. And therefore, I will have to provide some background information about both these areas. And today I will start with the background on random walks. And as I had said, I'm not assuming any prerequisites, and therefore I will start from very beginning. So I will, is this okay?
Yes.
Yeah, so let me begin with the definition of a Markov chain. This is actually a generalization of usual dynamics in the following sense. So we have a state space X, and for usual dynamics, we send points from this state space to this very state space. However, what we will do, we will assign 2 points from our state space probability measures on this state space. So I will denote this assignment by pi x. And this family of pi x is called the family of transition probabilities. Okay, and then the dynamics develops in the following way. At each step, we start from a certain point, but then instead of moving to a well-defined next point, what we do, we choose the next position randomly by sampling from the corresponding transition probability. And then once we arrive at the next point, we look at the transition probability from this point, and so on and so forth. So this is what is called Markov chain. Okay, now I will be talking about random walks on groups. And these are the Markov chains which are homogeneous in space in the most natural sense. Namely, now our state space is a group, which I assume to be countable. And well, I have this map, which assigns to any point the corresponding transition probability from this point. And then, of course, it is natural, once I have this group structure, to require that this map respects the group structure. So in other words, I want this map now to be equivariant with respect to the group action, which means that now I only have to define one transition probability at the identity of the group. And then for an arbitrary point, for an arbitrary element of my group, I just put the transition probability to be equal to the translate of the transition probability at the identity. Okay, and usually this transition probability is denoted by mu. So in other words, the transition probabilities are translates of a single measure. In other words, it means the following. So if we start from a point G, then the Markov transition consists in multiplying this point G by a randomly selected increment. And it is this increment that is distributed along according to the same law mu. So this is the description of the transitions of our random walk. And in particular, if we start at time 0 from the identity of the group, then at time 1, we will be at point h1, where h is the first increment, and so on, so forth. At time n, we will be at the point which is just the product of n increments. So here, all these increments were selected at each step independently and following the same distribution. Okay, so in other words, it means that if we want to look at the position of our random point at time n, then its distribution is nothing else than the n-fold convolution of the measure of the measure. Okay, so now, well, one should give examples. Usually, the first example of a random walk is the Poisson random walk on the integer lattice, but actually, first random walks were introduced by Poincaré some 10 years before Poisson, or rather Adamar, one should say. So Adamar, when reading Gibbs' book on statistical mechanics, noticed that shuffling cards can be a model useful for looking at the models of statistical physics. And then it was Poincaré who actually proved, well, the results about this model, convergence to the stationary distribution for shufflings, or in current terminology, it would be for random walks on finite permutation groups. Okay, so what are the examples? Let me write here. So example number 1. The group G is just finite symmetric group. Example number 2 will be, let's say, the Poisson example. Let's say z to the power d. So what happens in example 2? Well, here, in principle, one can choose an arbitrary probability measure, but one can also choose a nice one. So what does it mean nice? If we have a finite subset of our group, let's say K, then we can look at the probability measure, which is uniformly distributed on this set of generators. Okay, and the meaning of this is, okay, now I have a problem, because for some reason my pen doesn't go lower on the screen, so I have to move to the next page. So yeah, let's put dimensional lattice. Okay, and the way I am drawing this picture is that actually I am drawing the picture of the Cayley graph of the group Z2 endowed with the natural generating set. Okay, and then what happens? In this situation, our random walk has various interpretation, namely, since I'm talking about the measure which is uniformly distributed on generators, in terms of the Cayley graph, it means that at any point of the group, I'm just choosing one of its neighbors in the Cayley graph, and then choose this neighbor, one of these neighbors with equal probability. So in other words, I have precisely the uniform distribution on the set of neighbors, which amounts to the uniform distribution on the generating set. Okay, so this random walk, in this situation, the random walk governed by the uniform measure on the generating set, then coincides with what is called the simple random walk on the Cayley graph. So the random walk governed by this measure UK is the same as the simple random walk on the Cayley graph. So the simple random walk is the one for which the transition probability from any vertex are uniformly distributed on the set of neighbors. Okay, and now the third example, which will be, in a sense, opposite to the previous one, will be when our group is as non-commutative as possible. So let's take our group G to be the free group with two generators. Okay, and then, well, since this group has two generators, locally its Cayley graph looks precisely the same. Any point has four neighbors. However, globally, the picture is very different, because in this situation, the Cayley graph is nothing but the homogeneous tree of degree 4. So each vertex has four neighbors, and these vertices are organized to form a homogeneous tree. Okay, and now because of that, the qualitative picture will be completely different. So here what happens at each step, as before, we choose one of the neighbors with equal probability of 1/4. However, here, this graph is actually much more symmetric than the Cayley graph of the in the abelian case, because here we also have radial symmetry. And the group of rotations here is quite big. It is quite big, and essentially here, unlike in the abelian case, the distance is the only invariant for pairs of points. The distance is the only invariant for pairs of points. And the simple random walk, in this case, will respect this additional symmetry. Namely, if we look at the distances from the origin, then what happens when we perform our random walk? So each point has four neighbors. 3 of them are further from the origin, and 1 of them is closer. Therefore, if we look at the radial part of our random walk, then it moves to the right with the probabilities, with the probability 3/4, and it moves to the left with the probability 1/4. And this is what probabilists call birth and death process. So what we want to know about this process is, or, well, actually one can also gamble this way. One can also gamble this way. Well, with this way, it's actually profitable to gamble. So at each step, we gain 1 unit with probability 3/4, and we lose 1 monetary unit with probability 1/4. Of course, the result of this gain will be that your capital will grow indefinitely, which in terms of our random walk means that the distance from the origin will grow indefinitely. So the distance between, let's say, the identity and Gn goes to infinity. And now, since the Kelly graph is very special, since it is a tree, it means that we can actually switch from one branch of this tree to another branch of this tree, only passing through the origin of this group. But this we can only do finitely many times because the distance from the origin goes to infinity. And therefore, it means that our random walk exhibits non-trivial behavior at infinity. We have, for almost every sample path, Gn, we have a limit point, G infinity, which belongs to the boundary of these free groups. So there are many ways to define boundary in this situation. Since we're talking about the free group, one can say that this is the space of infinite words. Or since the Kelly graph is a tree, one can say that's a space of ends, or in a fancier way, one can say that that's Gromov hyperbolic boundary of this tree. So we have, here we have non-trivial behavior at infinity. And this is a very important qualitative invariant of the random walk, which is related to the notion of the Poisson boundary. Oops. Sorry. So what do we have? What do we have here? Let's look again at the previous situation. We have our group, our state space, and we have a certain boundary space. And then we know that the sample paths of our random walk converge at infinity. Therefore, on this boundary, we obtain the resulting heating distribution. The resulting heating distribution. And if we start, okay, let me denote it. If we start from the identity, let me denote it by nu. And if we start from an arbitrary point, G, then since everything is equivariant, the corresponding heating distribution will be the translate of this measure G nu, this measure G nu. So that's what is called a harmonic measure. So these harmonic measures are called harmonic for the following reason. If they satisfy the mean value property, indeed, if we are starting from the identity of the group, then in order to reach infinity, first we have to do the first step. We have to make the first step. And then we can present our point at infinity in the following way. We can present it as a combination of two random mechanisms. So first we choose the first random increment, and second we just start our random walk in U from the point where we are after this first random increment. And the result by the Markov property will still be the same. It will still be the same distribution at infinity. So in other words, it means that our harmonic measure will satisfy the following property. So I will write it in general. So the harmonic measure, which I denote by mu, is actually the average of its translates, taken with the weights given by the step distribution of our random walk. So that's a property, sometimes it's called mu stationarity. Mu stationarity. Mu stationarity. And now one consequence of this mu stationarity is the following, that if we take an arbitrary function on the boundary, write it properly, L infinity on the boundary, endowed the measure nu, then I can assign to this function its integrals with respect to the translates of my harmonic measure. And since the harmonic measures satisfy this stationarity property, it implies that the function f is what is called mu harmonic. And of course, it's bounded. So here I write mu. So what does it mean? It means that the value of my function f at any point is equal to the average of its values at the neighboring points, taking, of course, with the weights prescribed by our step distribution mu. Okay, so that's mu harmonic functions. That's mu harmonic functions. Okay, and let's look at this formula, which I have written here for the boundary representation of harmonic functions. I can rewrite it in the following way. So the value of my function f of g is equal to what? So I have to take the boundary function f hat. Let me write it with integral sign, and integrate it with respect to the corresponding translate of the harmonic measure. Or if I want to always integrate just with respect to the same harmonic measure, here I have to take into account the arising Radon-Nikodym derivatives. So what I have to do is that I have to multiply the boundary values by the Radon-Nikodym derivatives. And then all this I have to integrate with the harmonic measure corresponding to the identity of the group. And in this way, this formula looks precisely like the classical Poisson formula for harmonic functions in the unit disk. So this is precisely an analog of the Poisson kernel. Or actually, Poisson kernel is also written in precisely this way because the Poisson kernel is nothing but the Radon-Nikodym derivatives of the corresponding measures on the boundary. Okay, and now it turns out that this formula can actually be used in order to assign a natural boundary to the group, just using as additional data the structure of the random walk, this measure which provides the transition probabilities of our random walk. And here I have to well, maybe it's not so important nowadays, but there were times when one always had to explain why all of a sudden, if we want to just deal with groups, why would someone interested in group theory would all of a sudden start looking at Markov chains. Actually, there is nothing pathological here. And this is what one does all the time, because essentially what we are doing here is the same as what one does in Riemannian geometry. Because in Riemannian geometry, what one can do, one can just have a smooth manifold. One can look at this smooth manifold, but then one can equip it with an additional structure. So for Riemannian geometry, this additional structure is a Riemannian metric, or one can talk about other structures. Now, why Riemannian structure is the most interesting for me now is because if we have Riemannian structure, then it provides us with the Laplace-Beltrami operator. And this Laplace-Beltrami operator, in other words, provides us with the notion of averaging. It provides us with the notion of harmonic functions. And there is also a probabilistic interpretation of a Riemannian structure. A Riemannian structure is nothing else but a certain Markov process on the manifold, what is called the diffusion process. So if you wish, one can look, therefore, at the Riemannian geometry in the following way. If we want to understand smooth manifolds, then we have to consider diffusion processes on these manifolds, or maybe generating operators of these diffusion processes and the structures associated with these operators. And in the same way, if we want to understand groups, there is nothing bad in endowing our group with an additional structure, and then studying the group endowed with this structure. So returning to group theory, for instance, looking at groups as topological objects is now absolutely common. And whenever one talks about it, one doesn't have to start with an apology. And in the same way, here we are equipping our group with another structure, with this structure of an equivariant averaging operator. So once again, it's very natural. And from this point of view, studying random walks should really be considered as, on groups, should really be considered as a part of group theory. Okay, so now after this apology, how does...
Vadim, excuse me, a quick question. So on this slide, you have a boundary free group F2, and then you switch to the general group. So I guess whatever you're saying here, it's more general than just a free group.
That's what I'm going to talk now. Yeah.
Okay, okay.
That's precisely what I'm going to talk now. Okay, so in this situation, with the free group, what we had at the beginning was a group which was endowed actually with a bona fide topological boundary. And then we were looking at convergence of sample power to this boundary, which provided us harmonic measures and Poisson boundary. Okay, now it turns out that one can do it in the opposite direction. And namely, if we start from an abstract group, just from a general group, but endowed with this additional structure, endowed with this random walk, it allows us to equip our group with a boundary. So this is what is called the Poisson boundary. This is what is called the Poisson boundary. Okay, so how does it work? How does it work? Here, in our topological situation, what we had was actually the following. So we had a map which assigned to sample paths of our random walk the corresponding boundary point. Corresponding boundary point. This map was coming from the existing topological boundary. And now what I'm going to do, I'm going to look instead just at possible maps of this kind. And then it turns out that just existence of a map like this will be enough to construct the boundary. So the idea is the following. Let's look at all the, so what I'm dealing with here, I have my random walk, G mu, and this provides me the corresponding measure, P, on the space of sample paths. So for simplicity, I will just start from the identity. Then I take the first position of the random walk, the second one, and so on. So HI here are the increments of the random walk, and the sample path itself is denoted by G. Okay, and now I will be looking at all the maps from the path space to another space, let's say B, with the following property. I want this map to behave like the boundary map that we had in the case of the free group. So what does it mean? Well, first of all, I want this map, let me denote it by, let's say, B and D. So I want this map to be, first of all, measurable, which is, of course, which was, of course, the case in this situation, because here the boundary map was just a limit. Limits are measurable. And second, I want this map to be describing behavior at infinity in the weakest possible sense. Here, I just want this map to satisfy the following property, which is enjoyed by the usual limit map, which is the following. So if I have two sample paths, such that, or one can just say if I have two sequences, such that one sequence starting from a certain point coincides with the other sequence up to maybe a shift. So let it be sequence Gn, and this will be sequence Gn prime. Then, of course, if these sequences converge to limits, then these limits will be the same. That's a property of limit. And now I want my measurable map to have this property as well. Okay, so these are two very natural properties. And in a sense, they're really the minimorum of what one can require from a boundary map. And now it turns out, and this is the advantage of working in the measure category as opposed to the topological category, it turns out that actually there exists a maximal map with which satisfies these two properties. Among all the maps which are from the path space, which are measurable and have this property, there exists a maximal quotient map.
So you don't require any equivariance, so you don't impose any equivariance conditions.
Equivariance, no, it would, well, since we are talking about groups, probably, no, it will be automatic in this case if I'm talking about the maximal one. There exists a maximal map with these properties. In ergodic terms, actually, these properties mean essentially what I'm describing. I'm just describing the space of ergodic components of the time shift in the path space. And actually, Misha, to answer your question here, at this point, I'm not talking about groups. The same will be applicable to an empty Markov chain. Okay, so here, indeed, what does the second property mean? Second property means precisely that these two sample paths, they belong to the same orbit of the unilateral time shift on the path space. Because when we shift them, it means that we just forget about the initial segments and, well, the fact that they start coinciding, that they coincide starting from certain moments means precisely that their shifts coincide. Their shifts coincide. So, in other words, this space is nothing but the space of ergodic components of the time shift in the path space. Okay, and now it turns out that if we return to the harmonic functions, that this space actually provides a complete description of bounded harmonic functions. That's what we had started from. So the quotient space this is the oops, sorry. Poisson boundary. Namely, so what do we have now in these terms, in measurable terms? So here, at the very beginning, we had our path space. We have a quotient map. And as a result of applying this quotient map, we obtain a measure on the quotient space. So let me denote, so the Poisson boundary is d mu g. So mu denotes that everything here depends on our random walk. And it is endowed with the harmonic measure, which is the image of the measure on the path space under the quotient map. So in other words, that's a natural measure on the space of ergodic components. And now, how does the corresponding Poisson formula look like? It looks precisely as it was in the case of the free group. F of g is equal to the integral of the boundary values with respect to the corresponding translate of the harmonic measure. So this is how we, given a certain boundary function, obtain the associated harmonic function inside the group. Now, how does it work in the opposite direction? In the opposite direction, the best way to explain this correspondence is by using the Martingale convergence theorem, namely the fact that if we have a function f which is harmonic, then it means precisely that if we look at this function along the sample paths of our chain of our random walk, then this is a martingale with respect to the natural increasing filtration of sigma operators. And well, if our function f is bounded, then this martingale is convergent, and its limit, now I'm again referring to the notion of limit, its limit automatically will satisfy these two properties. Its limit will automatically satisfy these two properties. It will be measurable, and it will have this independence of the past property. Okay, so not only where was I interrupted?
So you talked about martingale, harmonic interpretation of harmonicity in terms of martingales. So, but
yeah, so we have a bijection. So in one direction, if we have a certain function on the boundary, then we can take its Poisson integral, and this will provide us with a mu harmonic function. And in the opposite direction, if we have a mu harmonic function, then its values along sample paths are a martingale. Therefore, they converge.
So why not you, Vadim, so explain in more detail what it means? So to be a martingale with respect to these values.
Okay, yeah, well, yes. Okay, so
and also, sorry, maybe a little even before that. So what do you mean here by a maximal map? There is a maximal map with this property. Maximal with respect to what? Could you say it, please?
Maximal in the category theory sense, so that if we have any map with this property, then it will be factorized through this maximal map. So what does it mean? So if we have another map with this proper, okay, let me erase.
The fibers of this map forms the maximal possible partition, true? So among all.
Okay, so
partition into fibers is the maximal possible.
Yeah. Okay. So it means that if we have a map with this property to a certain space B, then actually it means that this space B is a quotient of the Poisson boundary. Did I answer?
Yes, thank you. Yes.
Yeah. Okay. Now about martingale. So okay. Okay, where do I start concerning martingale? So suppose that we have an increasing family of sigma algebras, and in our case, this will be just the family of coordinate sigma algebras from 0 to n. Okay, and now suppose that I have a sequence of functions.
Just by cylinders of length n, true? So by
times between 0 and n. So I'm talking in terms of sample paths. Yeah. Suppose I have a family of functions, phi n, such that the function phi n is measurable with respect to the corresponding sigma algebra. So in our case, the functions actually depend just on the position at time n. So this is slightly more general. And then martingale is, this sequence is called a martingale if it satisfies the following property. If we take the expectation of the function phi n plus 1 with respect to the previous sigma algebra.
So in your sigma algebras are finite here. You just average over the elements of this.
Here, these sigma algebras, well, they're countable. They're countable, not necessarily finite. They're discrete, but it's not necessary. Yeah, so the Martingale condition is that this expectation of function with number n plus 1 is a function with number n. Okay, so this is actually more or less the best illustrated by looking at the conditional probabilities. So suppose that we have, let's say, we are talking about the unit interval. And the sigma algebra A, okay, I have used A, so let me use letter B. Okay, sigma algebra Bn is the sigma algebra generated by the order n dyadic intervals. Okay. And now suppose that we have a function on this interval 0, 1. Okay, and then what we can do, so let me draw a graph. So let's say something like this, yeah? And then what we can do, we can look at the conditional expectations of this function. So the conditional expectation with respect to the sigma algebra B naught will be trivial. It's just the integral of our function. So that's B naught. Now, if we take the conditional expectation with respect to the sigma algebra B1, so B1 consists just of two halves of our interval. And therefore, here we will have an approximation of our function by the step function of order 1. So there is one value taking on the first half of the interval, another value taking on the other half of the interval. So that's the conditional expectation with respect to the sigma algebra B1. Okay, and so on. So for instance, B2 then will be a function which is piecewise constant on intervals of order 2, something like this, and so on. And then it is precisely the Martingale convergence theorem which tells us that this sequence of functions converges pointwise to the original function. So it looks similar to the Lebesgue differentiation theorem, but in a sense, it's better than the Lebesgue differentiation theorem. Well, it's different, let's say. Why? Because the Lebesgue differentiation theorem just tells us that if we average our function along smaller and smaller intervals surrounding a given point, then we will recover the value of the function at this point. So here we are doing something similar, except for our intervals are not centered at our point. The intervals are prescribed, and we just at each step take the dyadic interval which contains our point. Okay, so in this sense, that's worse than the Lebesgue differentiation theorem. On the other hand, there is an advantage as well, because Lebesgue differentiation theorem actually is a non-trivial fact from the geometric measure theory. It's not true for an arbitrary measure space. To begin with, it's not even formulated in terms of measure spaces because one needs to specify how we are averaging, and that requires, let's say, a metric structure if you want to average with respect to both. And then it's a good question for which spaces one can really do it with respect to both. The unit interval, of course, in a sense, is a very special metric space. On the other hand, this Martingale convergence theorem or convergence of conditional probabilities holds. It's a measure theory effect. It doesn't require anything from the topological or metric structure of our space. So that's the advantage of which I keep emphasizing. This is the advantage of measure theory over all other theories. Okay, so yeah, and now to finish with this example, so if we look at this family of approximations, then this is precisely a Martingale. Because if we take the next approximation, the approximation of order n+1, and make it coarser, then what does it mean? It means that we took consecutive intervals of the same parity, so that the union is the interval of the previous level, and we average here, and we average here. So that's precisely this Martingale averaging. So the difference of conditional expectations is a Martingale, and essentially that's the main example of Martingale. So here, when I talk about this boundary correspondence, in the classical analysis, one uses Fatou theorem, which is a non-trivial fact. So if one has a harmonic function, a bounded harmonic function, then it has non-tangential limits. And here I do it all in the measure category. So instead, I'm claiming that if I have a harmonic function, then it does have limits. In the classical setup, I had to say non-tangential limits, whereas now I'm just saying along almost every sample path. And it turns out to be quite sufficient in order to establish this boundary correspondence. Okay, so now I have introduced the Poisson boundary, which is one of the central qualitative objects of this theory. And also I would need some quantitative objects, but it looks like my time is already up, so that maybe I will start.
You started, how long? You started 5 minutes late. You have at least 5 minutes, maybe 10 if you need. So,
well, not sure 5 minutes will be sufficient, but okay, let me try. Okay, so now quantitative invariance. Invariance. So here, yes.
Excuse me. The convergence that you use is you need L1. That all those functions random law are integrable and L1. So
no. L1 is not sufficient because if you have an L1 function, then the limit of the Martingale may be trivial. So in other words, good Martingales, which is what I haven't mentioned, good Martingales are so-called uniformly integrable Martingales, which guarantees precisely that one can pass the limit the space L1, that the integrals also converge. And this is why here which is customary in this theory, I'm talking about bounded harmonic functions. And of course, if my functions are bounded, then all Martingales are also bounded, and there are no problems with passing to limits under the integration sign.
Thank you.
Okay, so what are the quantitative invariants? So let's return again to the picture of the free group. So that's the calligraph of the free group. And here we see that the radial part, in this particular case, the radial part of our random walk also performs a random walk. So the transition probabilities are 1/4 to the left and 3/4 to the right, which means that in this situation, actually the distance from the origin will be growing linearly. And one can easily figure out what will be the growth rate. It will be equal to precisely 1/2. So the distance from the origin divided by n will go to 1/2. So here, once again, it's just because the random walk on the free group we're dealing with is very special. And in particular, its radial part is also a Markov chain, which is not the case in general at all. Now, if we are talking about a general random walk on a free group, or actually on an arbitrary group, then what we can do, we always endow our group with a certain metric. Okay, let me go back. So G endowed with a left invariant metric, for instance, word metric. And then what one can do, one can look at one can use this metric in order to evaluate how far we are from the origin. So one can look at the distance from the origin and ask the question how this distance behaves, And here, the first fact is the following. So I remind you that the distribution of the position of our random walk at time n is the n-fold convolution of our measure mu. Okay, so now I can just look at how far the points sampled from this distribution are from the origin. So I can look at the what in probabilistic terms should be called the first moment of my n-fold convolution. So what is this? This is just the average distance from the origin. Okay, so let me denote this number by Ln. And now, since I'm dealing with a left invariant metric, and my random walk is also left invariant, it easily implies that this sequence is subadditive. And here, sorry, it's Ln plus m. And therefore, if I divide these distances by n, then they will converge to a limit, which is called the rate of escape of our random walk. Rate of escape of our random walk. Okay, so now maybe I will at least formulate this fact. So I have defined the rate of escape just on average, and here I have used just the usual subadditive inequality. However, one can also define this rate escape individually along the sample paths of our random walk by using the famous subadditive ergodic theorem. Due to Kinkman. And actually, I think random walks on groups are really the most natural first application of the subadditive ergodic theorem. Okay, so what happens here? Let's look at a sample path of our random walk at time n plus m. So this is the product of n plus m increments. Okay, and if I want to find the distance from this product to the origin, which I remind just like this, so that's the norm induced by my left invariant metric, then by the triangle inequality, it won't exceed the length of the product of the first n increments plus the length of the product of the remaining increments. And now, if I'm looking at the corresponding space of increments, then here I can say this is the function, let's say phi n of my infinite sequence of increments. And this will be the function of the same kind with index m, because here I'm taking m increments, but evaluated not at the original sequence of increments. So h is just the sequence, h1, h2, and so on. The sequence of increments. So here I'm evaluating this function at the shifted sequence, shifted by n times the same shifted sequence. Okay, and in other words, and here on the left, in the same terms of this sequence of system of this sequence of functions, I have nothing but the function fn plus m evaluated at my sequence h bar. So we have this inequality, which looks like the usual subadditive inequality, except for its skewed subadditive inequality. Here I am also using my transformation T, which is the shift in the space of increments, the Bernoulli shift in the space of increments. And then it is precisely the formulation of Kingman subadditive theorem that if these functions are integrable, for which it is enough to require that the function phi1 is integrable, namely that just one-step distribution, just that the measure mu has a finite first moment, then we know that these functions phi n evaluated at sequence h divided by n converges to a certain limit almost everywhere and in the space L1. Well, since this shift is Bernoulli shift, it is ergodic, therefore the limit must be a constant, and therefore it must be precisely the same constant as the one which we have found here by considering just the integrals of those functions each. So converges the number which is called the rate of escape. Therefore, there are two definitions of the rate of escape. There is definition on average, which doesn't require anything, just the triangle inequality, which says that the average at time n divided by n converge. And we also have a finer version of this theorem, which said that this convergence also holds almost everywhere. If we are taking almost every sample path, then its distance from the origin divided by n, or in terms of the increments, the length of the product of n increments divided by n converges to the rate of escape. So in the, this result is also quite often used for matrices, where it is actually what is known as Furstenberg-Kasten theorem. Furstenberg-Keston theorem, which says the following. It's essentially the same. So if we have a product of random matrices, then if we take their norm, and since the matrix norm is multiplicative, one has to take the logarithm, then divided by n, it converges to a limit almost everywhere. So that's actually another interpretation of this result. So Furstenberg and Keston proved it before Kingman when the subadditive ergodic theorem wasn't available, but this is really the most natural application of the subadditive ergodic theorem.
So in case of matrices, you're dealing with non-discrete group, or you are?
Doesn't matter. Well, for the distance here, I don't need discrete groups either. Actually, it's so far it's completely general. The only place where I would need groups to be countable is where I define the Poisson boundary. There, if the groups are not countable, then there are certain measurability issues, and one has to impose conditions on the measure. For instance, one should require, for instance, that the measure is absolutely continuous with respect to the hard measure. But in what concerns these quantitative invariants, there is no issue here.
So what is the general setting for this kind of results? So if it is not discrete,
for this kind of results, well, you just have a left invariant, it doesn't even have to be a metric, a left invariant subadditive function. Left invariant subadditive function. Because here you see Kingman's theorem, it's formulated entirely in the measure theory. It doesn't require anything except for integrability of the involved functions. And therefore, whenever you can write a subadditive function, subadditive in this sense with kind of skew subadditive, then the subadditive theorem holds.
so, but what are the assumptions on the group? Just topological group with measure, or just what is the general assumption that you impose on the group?
Here you see, I don't think. Okay, the way I would formulate it is the following. So I really would start formulating it from the ergodic end. So I just have a certain measure-preserving transformation, and I have a subadditive sequence of functions. And then if I can interpret the state space of my transformation as a space of certain sample paths somewhere, then I have subadditive ergodic theorem. So for instance, one can also do it for, let's say, Brownian motion on foliations, or for random walks on equivalence relations, or as probabilists like to say, for random graphs, random walks on random graphs. So really important structural element here is the presence of a measure preserving transformation of the path space. So, or one can talk about, let's say, random products in groupoids, or heavens forbid, in hypergroupoids.
Okay, it's enough. Thanks.
So, Vadim, did you finish your talk, and we can move on?
Yes, I think that's
Okay,
enough.
well, let's thank the speaker. Are there questions, comments?
So what will be the program for the following lectures?
Okay, so the next time I'm going to finish with general theory of random walks. So I will define the entropy, and then I will discuss the relation between the entropy and the rate of escape, what Anatoly Moiseyevich calls the fundamental inequality. And then I will switch to the self-similar part. So I will define self-similar groups, and then I will start talking about random walks, but this will probably be already lecture 3.
May I ask a question, Vadim?
Sure.
So my question is following that basically you can interpret what you were discussing, this random walks, as a general setting of random dynamical systems plus algebraic structure there.
Yes.
And in the general theory of random dynamical systems, there is a notion. So if you have stationary distribution, any stationary distribution for the corresponding Markov chain, then there is a set of conditional probability distributions naturally defined for infinite past, which is analog, I guess, of the boundary type of thing.
Yes.
And so in your case, of course, you have a very distinguished stationary distribution, which is Harmonic measure. And then is it possible just to say that what you construct is just these conditional distributions, which are Martingale construction for this measure?
No, a little bit different. No, stationary distribution is not a Harmonic measure.
For the Markov chain on a group, Markov chain will not be stationary distribution?
Well, it is it is trivially stationary, but it is infinite, so it's not interesting. It's no, the right stationary distribution, and it really plays an important role here, is the distribution on the Poisson boundary.
I see.
Is distribution on the Poisson boundary, because here, and it can actually be interpreted in the terms you are mentioning, because here I have used this space of increments. And here, so far, I have been talking only about unilateral space of increments, so only increments with positive indices. But it is very useful and very convenient to consider actually bilateral space of sequences. And then one has conditional distributions in pretty much the same way as you mentioned.
I see. Okay, I understood.
So, but the final goal for you, Vadim, would be amenability. The final goal would be something like amenability for the Basilica group. Will you get that far? So what would
the results essentially, yeah, I will. The main application is this one. Well, I will mention some more examples, which are actually, it's not complete results or rather questions, but I hope you won't mind. But ultimately, well, talking about rescaling or renormalization, so far, the only results are indeed proofs of amenability of various groups, yes. But of course, the area is by no means exhausted by these results, but maybe here one should look at the conditional distributions in the future.
we will?
Okay, thank you.
Could you comment on how sensitive is the Poisson boundary to the generating set of a group? So
that's a big question. That's a big question which deserves. Okay, so what happens is the following. So the way the Poisson boundary is defined, it's defined as a quotient space of the path space.
Yeah.
And therefore, a priori, if you have two different measures, two different random walks, then there is no way one can naturally link one Poisson boundary with the other Poisson boundary. One can do it if these two random walks are somehow related to each other, which sometimes happens, but in general, well, there is no way they should be linked, because here we're in the measure category, and in principle, we have this notion of singularity, which says precisely that if you have two singular measures, then they don't know anything about each other. And here it's pretty much the same. So if we have two different random walks, then the Poisson boundaries, a priori, they don't know anything about each other. However, there are questions about which I will rather talk next time, which are still open about how rough these dependence can be. So here the theory is different because there is L2 theory of random walks or of Markov chains, which is responsible, for instance, for recurrence. And the L2 theory is quite robust. It's quite robust, and there is a lot of results saying that various L2 invariants, they behave nicely with respect to quasi or rough isometries. Here, there are examples showing that it is violated if one talks about graphs. So there are examples when we have a graph, we change something quasi-isometrically, and then the properties of the Poisson boundary change drastically. Now, in those examples, there is no group invariance. For groups, it's still a completely open question, but I personally, I don't believe that it should be true. Maybe we are just not sophisticated enough to construct the corresponding counterexamples. But in general, I do not believe that there would be a rough or quasi-isometry invariance in this L infinity theory, unlike in L2 theory.
Other questions, comments? If not, let's thank the speaker again.